SIP endpoints, and they can be server or clients. This is standard SIP terminology for user agent server and user agent client. And the client is the one that initiate a call. The server is the phone that is answering a call. So while we are normally thinking of phones as clients, actually they can be both the client and servers. OpenCPS in this architecture, in the SIP standard architecture, acts as a proxy, so it routes the packets, it routes the signaling between the endpoints, so between the phones. Phones sends a message that is directed to another phone, and to reach the other phone, it has to, first of all, knows where the other phone is. And so it has to pass through a register. And this is the second function of OpenCPS. So the phones will take care of talking with OpenCPS, asking where is the other phone. And then when they know where is the other phone, they will send OpenCPS a message that OpenCPS will take care of route to the other phone. So in this architecture, as you can see, OpenCPS never touch the media. We are talking about only signaling, only addressing. Then we have the FreeSWITCHs. FreeSWITCHs stay at the back end of our architecture, and they take care about all the back-to-back user agents. So what is this back-to-back user agent? This is an important term, and it's like FreeSWITCH is two phones at the same time. So it's two phones like back-to-back. They, from one side, FreeSWITCH accepts a call, an incoming call. From the other side, it originates an outbound call, and then it bridges the two calls inside himself and mixes the audio, and mixes the video, and mixes the media. So let flow the media back and forth between the two endpoints. So those are the three elements. All the problems about scaling an architecture depends on mismatching between the addressing, so the plain network addressing, and the media addressing, so the addressing that is contained in a specific part of SIP that's called SDP, Session Description Protocol, where the media endpoints are described, that are not the same like the network endpoints. So what is to be done? This is a most important phrase that sets our agenda for the next decades. So we're interested in creating an architecture that takes care about security, high availability, and then its functions are registrations, presence, making internal calls between our in-house endpoints, make external calls between ITSPs, DIDs providers, the external world, so PSTN, cellular networks, whatever. Then we need to be able to manage special cases into how we manage calls. Because, for example, there are corner cases in conferences, in queues, in call centers, in call transfers, and in many other cases where the call cannot be on a random machine, but needs to be in a specific machine because other calls are in that machine, and you need to be in the same machine too for the audio or for the media to be mixed together. So we will see each one of those cases, and at the end of the presentation we see how OpenSpace and FreeSWITCH can deal with NAT in the case where you are implementing a PBX in the cloud as a service for external customers. So when you have the phones that are not on the same network as the FreeSWITCH phone. Security. We implement our external edge as a session border controller, SBC. Whatever this means, it's because SBC is just a marketing terms, and actually it doesn't mean nothing or means something different each one you ask for. In our terminology, the terminology we want to use here is that we restrict completely our area of exposition to the bad internet. So the only point that we expose is one only IP address and a restricted number of ports and nothing else. All that is behind that unique border with the internet is on internal networks that are unreachable, unroutable from the internet, so that are not exposed to attack, to denial of services, and to spoofing and other kind of problems. So it's much easier to secure and to manage. And you manage this with standard techniques, very well-known techniques like port forwarding, IP tables, firewalls that can be also embedded firewalls, so hardware firewalls. And you use as the first line of defense on your OpenCPS that are facing the internet, you use modules like Pike, like the anti-fraud modules, and you do all the checking on packets that are well formed, that are not doing some buffer overflow, but also that are respecting what are the grammar of SIP. So you are taking advantage of the structuration of OpenCPS to check that all is okay. Then, high availability. You want to have continuity of service whatever happens. So what you do is you double your OpenCPS and you have a very standard, very traditional active-passive configuration. In all this presentation, I'll be very, very conservative, and we'll be speaking about the very basics and the very important techniques about scalability and clustering. Then, obviously, we have seen that with the 2.4, we have the capability of having all the OpenCPS working at the same moment, active, as a big sharing all the backend data between them. We will not touch this in this presentation. We will see how we can have in a more traditional active-passive way that where two machines running OpenCPS can have one virtual IP address that is moved between machines by Keep Alive or DRRP, CARP, or whatever kind of protocol for high availability that acts when you have a periodic check that checks if all the SIP infrastructure works. So it's important that you check not only that OpenCPS is running, but that OpenCPS is answering correctly, so that all the chain is working. So OpenCPS can correctly connect to the database backend, that then can connect to the FreeSWITCH backends. So the best thing is to use some tool like SIPSec or some homegrown tools to check that you can actually make a call or at least answer a simple message. Then you manage the results from this checking of a SIP working with the three kind of scripts. One that is promoting that OpenCPS to the active, to the master role, another that is demoting it to the slave, to the backup role, and another one that is just taking care of tearing down the machine because that machine is not working. All the SIP farm has not this kind of architecture in active passive. They are all active and they are load balanced. So their high availability comes because we have many of them, and if one of them goes down or more of them goes down, it's not a problem, we just spin up another machine. So this is very poor graphic, but give us an idea of how it works when we have the OpenCPS and the FreeSWITCH farm on the same network. So we have here, this part is the external network. This is the internet where the wild jungle is. And we have here our ITSP and our DID provider that certain times are the same and certain times are not. And we are exchanging signaling and media with the ITSP that comes on the external part, and this is our bastion, this is our OpenCPS, IP tables, firewall, and whatever. This is our front end to the external world. Then inside, we have on the same network, we have our FreeSWITCH farm with our phones. So actually, the phones are able to exchange signaling with OpenCPS, but then are able to exchange media directly with the farm. So, registrations. Registrations are the most important function that we move completely, almost completely, from FreeSWITCH to OpenCPS when you begin to grow FreeSWITCH. That's because you want to have the registration as a high frequency transaction. You want the phones to continue to register in the shortest span of time that you can bear. That's because you want your inventory of the phones, where they are, if they are up, if they are down, the most recent and the most current and the most accurate possible. So you don't want the phones to register once in an hour, and then you try and you think that they are up and maybe they are down, and you try to push calls to them. You don't want that. You want a frequency of registration like 1 minute, 2 minutes, or something like that. If you have a robust number of phones, this can be very taxing on FreeSWITCH, very taxing. That's because of multiple factors. But the most important two factors are that FreeSWITCH used the SOFIA stack to manage SIP, and the SOFIA stack is not geared toward high volume registrations. So you can mitigate this using a specific configuration option that is that each registration will have its own thread. But this, on the other side, will use a lot of resources because obviously it generates a thread, an entire thread for each registration. And the Sophia stack is a complete end user client stack that is kind of heavy to be spawned for each one registration when you have, let's say, 5,000 phones or 100,000 phones that registers each one each minute. So what you want to do is to have the phones to register to OpenCPS. Why this? Because OpenCPS has been written a low level, very low level, to use the maximum efficiency just to manage registration. That's in itself, because for FreeSWITCH registration is nothing, it's the minimum building block. While FreeSWITCH is optimized to do high CPU intensive works like mixing media, like doing difficult business logic, while OpenCPS is designed for having the most important number of transactions in the fastest and lightest way. So what we want is to have the phones to register to OpenCPS, and then to have OpenCPS that in some way will let FreeSWITCH know. What you choose to do that, we will see that the OpenCPS developer has the perfect solution for that. It's called the mid register, and we will see it. But let's see what is a registration. A registration is when you put in some database where a SIP user ID can be reached. So what is the IP address of some user ID, SIP user ID? So we can send call to him. And what we do is we have the phone to register to OpenCPS. So OpenCPS gets the real address, the real IP address of the phone. That can be on an internal net or external net. Then OpenCPS will send periodically, but one time each hour, to FreeSWITCH and with its own address. So FreeSWITCH will think that the phone is registered at the OpenCPS address. So when FreeSWITCH want to reach the phone, will send messages to OpenCPS. Then OpenCPS will take care of routing these messages to the phones. Why we want this? We want this because this way we can have the lowest possible processing. So we just dispatch the registration one time each hour to a random FreeSWITCH server. The FreeSWITCH server, they have their database in common. They share the database, and they will be aware of this. And the OpenCPS, when the phone is not respecting the registration expiration, so for example, the phone is expected to register one time each minute, then is 2 minutes that is not registering, then OpenCPS will take care of telling FreeSWITCH, oh, this phone is no more registered. But this will create another message that will just wake up FreeSWITCH and tell him this phone is no more registered. And if not, we will have one message each hour. So it's like 60 times less messages as a volume. And we will use the OpenCPS MIDI register, user location, and dispatcher modules, and the NAT helper in the PBX in the cloud scenario. Then we have all that is related to presence, BLF, shared line appearance, instant messaging, message waiting indicator, all the things that are more presence, simple options and things like that. And the rule of the thumb is, if you don't have a real huge volume of traffic for this kind of accessories, it's better to leave it to FreeSWITCH, because FreeSWITCH is geared to manage this kind of traffic in an integrated way with its own PBX functions. If you have a real high traffic, then use only OpenCPS to manage this presence and then don't try to mix it. Don't try to have an half-legged, let's say, solution, because that will bring problems. And now we're going on the meat of our architecture, so we will see the different case with calls. And what is a call? A call is made by two messages, one invite and one answer to that invite. Each one of those messages is composed by two addresses that are the addresses where the clients are located, and one media address that say from where you can get the media, the audio or the video. Problem is that often those addresses are not the actual addresses, because, for example, the phone is behind some NAT, so the external address is not matching the internal address, but when the message is sent, the pure addressing will be taken care about by SIP itself or by the firewalls. Problem is the internal media addresses that is written, unfortunately, as text and as an attachment, let's say, to the SIP message into the SDP part, the session description protocol, then will not match, and you will have those kind of calls where you can hear but the remote part can't hear you, or all these kind of problems that we've seen so many times. So, how much time I have?
5 minutes.
5 minutes.
6. I'm saying 5, so you got a minute of questions.
Okay.
So.
Okay, good. We will not go to the end of it, obviously, but let's have an idea at least. FreeSWITCH use two main labels, let's say, to divide its own SIP dealing with the external world. Those are called profile, and each profile is a pair of its own internet address and a port. So, for example, I am 10.10.10.1 port 5060. And this is one profile, and traditionally in FreeSWITCH parlance, the internal profile is in port 5060 and is dealing with the in-house phones. And that's a trusted environment where all the features are built into the dial plan, and where the phones are able to reach for pay services, for example PSTN gateways or other kind of for pay services. You don't want in no way to have your internal profile, your internal network that is reachable from the internet, because this will lead to void fraud. Fundamentally, there will be some gangster from the internet that will route through your network a lot of traffic that will go to the PSTN. They will sell this traffic and you will pay your ITSP for this traffic. So you don't want this, and you want this this interface that leads to the internal profile to be hyper secure on another network, not routable from the internet, etc. etc. So the internal phones register and deals only with OpenCPass and exchange signaling on port 5060 with OpenCPass. And FreeSWITCH knows that the phone is registered at OpenCPass address, so when FreeSWITCH want to send a call to a phone, actually it send a call to OpenCPass, and OpenCPass will on its own send a call to the endpoint to the phone. And so this is the most simple possible call that involving one only phone. So the internal phone call a FreeSWITCH service, for example an IVR inside FreeSWITCH, and the phone will send its own media address into SDP to the port 5060 of OpenCPass. OpenCPass will send this SIP message that has the media address of the phone to the FreeSWITCH port 5060 that corresponds to the internal profile. Then FreeSWITCH will match what is the addressee, the called destination, the destination number, and will match into its own dial plan, and we'll see that this destination is the extension of the IVR, and FreeSWITCH will start playing some sound and some media to the endpoint, and the media will flows from the SDP or phone to the FreeSWITCH SDP, while the signaling is passing through OpenCPass. In this case, we'll see how it works for two internal phones. So my phone and my colleague phone, we are both in-house into our company, and we are talking each other. And in this case, it's just like the first internal call, but it's double. So it will go from my phone to OpenCPass, from OpenCPass to the SDP of FreeSWITCH. Then FreeSWITCH knows that this call is for the other phone. So what he do? He originates a call, makes a new call with another one SDP of its own. So it's the second FreeSWITCH SDP that is sent back to OpenCPass. OpenCPass knows that is for phone of my colleague, and then back. So the media flows from the SDP of phone A to the first SDP of FreeSWITCH, to the second SDP of FreeSWITCH, to through OpenCPass to phone B SDP. In this case, let's see that the signaling will be like this, this, while the SDP will be this and this. In this way, we are implemented two calls that are back to back and mixed. The media are mixed inside FreeSWITCH. Then we have a different scenario when you must interact with the external world. So when you are pushing a call from your in-house phone to the PSTN. I will go very fast on this, but the concept is the same. You will just pass through the RTP proxy to reach the external. 1 minute.
Yeah, that's it.
Okay.
Questions?
No. And it will reach. The important things in this case is that we are using two different FreeSWITCH profiles. One profile is the 5060 that will always be used to deal with the local phones. The other profile is on port 5080 and will be the one that deal with whatever is external. So in this case, with the external ITSP and DID provider, but in any case, passing through OpenCPass. 30 seconds more, and okay, the media flows from the DID of the DID provider server, the DID SDP, to RTP proxy that is managed by OpenCPass on our bastion, on our facing the internet, then to the external SDP of the RTP proxy, pass to the internal SDP of the RTP proxy, because RTP proxy also is like a back-to-back, so gets the packets from outside and send the packets to the inside. He wrote it. Then from the internal SDP of RTP proxy, it goes to the first SDP of FreeSWITCH, then to the second SDP to FreeSWITch, then to the phone SDP, and then back. So passing through the FreeSWITCHes, then the OpenCPass, then the RTP proxy, then the ITSP or the DID provider. The last things you will see in the slides, because I will not take time to tell you, but the most important things when you do this kind of architecture is taking care of all the corner cases. So all the times that you want the calls to be on a specific machine because you have good reason for that. For example, because you want to mix the media, or because you want all the calls that are originated or that are incoming to a user to be on the same machine, so that user can do things. And then we have the NAT things, and we will deal with NAT with FreeSWITCH, with OpenCPass. Those are the books about FreeSWITch. I auto-read all of them. I'm available.
Breathe.